Alright, let's give this a go. So last week we had a look at the solving and sketching of exponentials. This time we're going to do the flip side of it. We're going to have a look at the solving and sketching of the logarithm. So let's dive in. So logarithms, what's going on here? Well, the logarithm and the exponential are directly related to each other. They are actually inverses of each other. If you look at what those graphs end up looking like, they are reflections across the line y equals x. Right, so you've got the exponential in green here, we've got the logarithm in blue here. You can see how they are mirrored across that dotted line, which is the line of y equals x. As for how you get from one to another, basically put, any exponential statement can be rewritten into an equivalent logarithm statement by just flipping the terms around. So you've got a y, an x, and the a for the exponential, or essentially you have the base and the exponent. The order in which you flip things around is the base of the exponential becomes the base of the logarithm. That's that bit there. From there, whatever the exponential was equaling goes in the brackets of the logarithm, and whatever the exponent was is going to come out on the outside. We've looked at this a couple of times before. One of the applications of doing this is simply to solve for x, right? If x is in the exponent spot, it can be quite challenging to solve for it without using logarithms. If you flip to an equivalent logarithm, you can see that the x is going from in the power to now where we would expect to, or where we would want it to be. We can start doing some algebra related. As an example, we have a statement here, 6 equals 4 to the power of x. Expressed as an equivalent logarithmic statement, we have log 4 6 equals x, right? Base of 4, log 4 equals 6, 6 goes in the brackets, power of x, power of x. Any questions on the rearranging of that so far? If so, let me know. Otherwise, this is just detailing how and why that is the inverse, right? So if we think about how we do inverses, you always start by swapping the location of the x and the y, and then rearranging to get the y on its own. So if you do that for the exponential, instead of having y equals a to the power of x, you now have x equals a to the power of y, right? You flip the location of the x and the y, respectively. Then from there, the only way to get y on its own is to convert to the logarithm form. So, having done that, you can now see y is on its own, and it's equal to log ax. Inverse of a to the power of x is therefore log ax. Most of the notation you'll see for logarithms is going to be either log with a base of e, which is referred to as the natural logarithm. E is a special number, kind of like pi. It's an irrational number, roughly 2.7-ish. It'll either be written as log e or just natural log, ln. The other one you might see is log base 10, which is sometimes written with a capital L. I don't think that appears in the textbook at all, but I have seen other sources, or certainly like university sources will definitely use capital L, or have been known to use it before. So if you see just capital L for log, you have to assume it's base 10. That's just on the off chance that you see it though. Next up, so one of the main things you do in the logarithms area of study is do the algebra that is specific to logarithms. So kind of like how we do the similar thing with exponentials and index laws, there is the equivalent way of expressing that with the logarithm. We have our product, quotient, and power laws respectively. All of this simply tells us ways of algebraically manipulating our logarithms. So the product law basically means if I have an addition of two separate logarithms with the same base, then I can replace that with a single logarithm with the same base that has the product of each of those terms in the bracket. M times n goes in there. Similar with the quotient law, if there's a subtraction between them, it becomes a division instead. Definitely worth highlighting. These log laws are only applying for logarithms that have the same base. If this was log 2 and this was log 3, you don't suddenly get like a log 5 or anything like that. They just flat out will not combine. So you have to make sure that they have the same base. At least for those two. The power law is kind of one where you pretty much do it in isolation. Essentially, if you have any coefficients on your logarithm, they can be brought into the brackets as a power of that entire bracket. And vice versa. If you have a power, you can bring it out on the other side. All of these are bidirectional. Usually you're using the right-hand side into the left-hand side, but we've seen applications, in fact, I think in the review class we saw an application of starting with the big logarithm and then expressing it all the way out, or expanding it all the way out, like this one here. This is a product of 100 x cubed and y to the power of -half, and a division of y squared. You can take this big logarithm and spread it out across multiple terms based off of the product and quotient laws. Those are the log laws. The next up is the logarithm identities. Similar things. This is mainly used in the simplification of your final answers. They're less about manipulating the actual algebra of things and more about evaluating what the logarithm actually would be. Starting with log a of a is equal to 1. So basically put when the base and the bracket of the logarithm are the same. So if you had like log 2 of 2, log 3 of 3, any identical base and bracket, that will always equal 1. The other thing worth highlighting here is that every law that we look at, or identity that we look at, is going to be proven by the same method. And the reason I mention that is because some of these will look quite similar. Like log a of a equals 1 and log a of 1 equals 0. It reuses a lot of the same terms there, so it can be kind of difficult to remember which one's which. So having a general purpose way of figuring out what's what is going to be good to have. So let's have a look at how we can prove these laws. The way you start is to start with the logarithm statement and just say, okay, I know log a of a has got to do with something in here. Let's just call it y. It's going to be equal to something. Let's call it y. From there, convert your logarithm statement to an exponential form. And the reason we do that is because evaluating this, or thinking about what that's going to be, is a lot easier. Right? A to the power of y equals a. Well, the only way that's going to ever work is if y is 1. Right? A to the power of 1 is the same thing as a to the power of 1. So if you ever forget what do you do with log AA, let it equal y, flip to exponential, and then that'll allow you to evaluate what that y should actually be. Because remember, y is the logarithm that we started with. We'll see another example of doing that here. Right, the other identity, log a of 1 is equal to 0. So as long as the bracket is 1, the logarithm will always equal 0. Again, if you forget how that is, just say, okay, I'm pretty sure it's something, so let's just make it equal to y. Flip that to exponential, and then think about what y would have to be. In this case, any power, a to the power of 0, is going to give us 1. So if a to the power of 0 gives us 1, then y should be 0. And if y is 0, then log a of 1 should be 0. Is there anything to be clarified around proving these? You don't need to prove them, it's more so just getting you to remember which one's which, just in case you forget in the real thing. Any questions on the proof? Cool. Next up, a few other things, less equations, more just properties of the logarithm. If the brackets of the logarithm are negative, there is no real solution for that. If we look at the graph of what the logarithm is, with no other transformation terms in there, we can see it has a vertical asymptote at x equals 0, and it's not defined for anything left of x equals 0. So when you have, when you have a negative in the bracket, you're going to get a non-real solution. As for why it becomes non-real, again, let's have an exploration. So let's assume we have some negative number in there, and I don't know what it is, but we're going to call it y. Flip that to exponential, and we're going to have a think. A to the power of y equals negative b. Now, technically speaking, there is a world in which this could be solved. and that's only if the base was negative. But base being negative is definitely not something we look at in methods. In fact, we don't look at it in Spec either. And the reason why is because the graph that comes out of it is very wonky. You start getting into really strange things because you're raising a negative number to a power, so it very rapidly changes between positive and negative results, as well as non-real results when you have your roots, any fractional powers along the way. It's a very, very complicated graph. In fact, if you get your CAS to try and graph it, pretty sure it'll just break, or it'll do some weird shit. I'll, just out of curiosity, have that cooking in the background on the handwritten bit, should you want to see it. You can see how it's just diverging all over the place. But okay. Oh, I actually had some of that written down as well. Yeah. Anyway, next up. If the bracket is 0, the logarithm is undefined. So that's a distinction that that matters for Spec kids. So the difference between non-real and undefined is important to understand for anyone who's doing Spec here. Non-real just means it could be an imaginary or complex solution, whereas undefined just means literally it's undefined. We haven't given it a definition. This is typically reserved for like your asymptotes, right? So if we remember again, this x equals 0 asymptote, we can only ever approach it. We never actually equal it. That's where you see undefined used. Why is it undefined? Well, let's have a look. Log a of 0, we don't know what it equals. Let's say it equals y. Well, flip into exponential, we're going to get a to the power of y is equal to 0. Which, if we're familiar with our exponential studies, a to the power of y being equal to 0 just doesn't really happen. If you look at that green graph, it only asymptotically approaches 0 but never actually hits it. So for that reason, undefined. We'll never actually hit it. This one comes in handy a couple of times. So you'll notice it when it comes up because it's such a weird thing, right? Like, when do we ever have a logarithm in the exponent of an exponential? So the cases where this does become relevant, you'll know immediately because it's very rare to see that in there. The property is as follows. If you have the same base exponential and logarithm, where the logarithm is in the power, so you can see how they both have the same base of a, whatever's in the brackets that logarithm is the answer. So if this was a to the power of log a 10, that's just 10. Reason why? This one's going to be a little bit different to prove. So we're still going to flip whatever our result is to exponential form, but rather than try to evaluate what does y equal in this situation, we're going to actually just shove y back in as that logarithm. Alright, we start here, we flip to our exponential form, and then we still know that y is equal to log ax. So let's just slap log ax in there. And suddenly you get, well, exactly that property. You derive that formula. Again, you don't need to know how to prove these. It's just kind of nice to know where it comes from. Gives you another way of remembering what to do. Okay. I'm going to leave this. Yeah, let's leave this for later. I've got this in here because I thought it was useful for a couple of questions, but since writing this, I found that you don't ever really need to do this. There's other ways of going about it that solves it better, using just the other stuff we've talked about so far. So if you guys are interested in this, I do have like recorded versions of these lessons, or shoot me a message and we'll cover it in maybe like a review class if you're interested in it. But we shouldn't need to have a look at any of them. There's other ways of solving those kinds of questions. Yeah, that's it for the fundamentals here on how logarithms work, the log laws, log identities. All of this is simply there to either help us solve our exponentials or help us condense down logarithms into a nice, easy, well, at least a nice and neat answer. Any questions on how any of that works so far, or shall we just move into some examples to practice? Okay, I'll get a screen grab of this. That way we know what thing's going to be relevant. I'll put that in the chat. Okay, where's a decent place to start? A lot of these are kind of similar, huh? Let's go with something like this for A. Okay, I'll pull out the digital notes and we'll go off of that. Okay. So for A, we got half log 10 bracket 16 plus 2 log 10 5. All we're trying to do is simplify this all the way down into one nice final number, or final logarithm. What could we start doing? You've got the screenshot of all the log laws and identities that you could potentially be using. There's one thing that we definitely have to consider at the beginning, and that is that all the log laws that we use assume same base, yes, so they both have a base of 10, which tells us we should be able to use all our log laws. The other thing I didn't quite highlight was that any coefficients on the logarithms can actually start making life a little bit harder. So for instance, this one's got a coefficient of half, this one's got a coefficient of 2. It can be a bit complicated to imagine how those are going to combine, especially if the brackets are different as well. Because this is saying we have half of log 10 of 16, and this one's saying we have 2 of log 10 of 5. So it's not like we can just sort of combine these coefficients, 2 plus a half. We've got to do something to either, we've got to do something to remove those. And there's only one way to do that. That's going to be using the power law. Right, so that's the third of the log laws there. Log a of x to the power of n equals n log a x. So with that in mind, all of these coefficients here and here can be brought into the brackets as a power of that bracket. So pretty much always is a good place to start with this logarithm condensing stuff is to bring any coefficients in as powers. That's going to give us log 10 of 16 power half plus log 10 of 5 power 2. Now that there's no coefficients involved, we can maybe see how the product law and quotient law are going to be a lot more easier to use, right? If you notice the definitions of them, or the equations of them, none of those have or show you how to handle coefficients. So the natural step for that would be to remove those coefficients. That way we can now use the laws appropriately. We can even step things as simplify things even further. So we got log 10 16 power of a half. 16 power of a half, to remind ourselves from our index law stuff, power of a half just means the square root of a number. So in other words, this is square root of 16, so just 4. Then we also have log 10 of 5 squared. We should all hopefully know that one. And now finally, we have an addition between these two logarithms. Only one of these log laws is going to be relevant here. And that is going to be the product law. Right, you've got this addition between the two. If you look on the screen share, it's the first one on the list, right? Log a m plus log a n. You can combine those into a single logarithm that is the product of the two. So in other words, log 10 of 4 times 25, log 10 of 100. And that gets us a nice and neat answer, though it's not a final answer. We have so far just combined it all down into a single logarithm. This can go further, and there's a couple of ways you can do it. Anyone want to suggest a way we can finalize this answer? We could do it with log laws and index laws. You could also do it just by understanding what the logarithm actually is. As a way to evaluate logarithms. We didn't touch on it today. Cool. So the most direct method for this is to simply just evaluate the logarithm. So any logarithm statement is basically just saying, what do I have to raise this number to the power of to make it equal this number? That's all it is. So 10 to the power of what gives us 100. 10 to the power of something gives us 100. Well, the only outcome there is going to be 2. So this one does simplify to 2. As for how to do that in like a log laws approach, well, one of the things you could potentially do would be to convert this down to 10 squared. Use your power law to bring that 2 out the front. And then use the first identity, which is that log a of a, or log 10 of 10, equals 1. 2 times 1, 2. So it's just like algebra. There's multiple ways of getting to the same spot. Obviously this is longer, but you might consider doing this when you don't have numbers to work with, if you have letters to work with perhaps. Any questions at all on those? That was a fairly fundamental one. We explored just a few of the laws as well as some of the identities there, making sure we get the coefficients in as powers and using the product and quotient laws from there to simplify things further. Cool. So there's a bunch of different questions that take that to extremes. The one that we looked at in the review was question 7. Log 10x equals a, log 10y equals c, and then express this nasty big thing in terms of a and c. We won't have a look at that one today again. We did that in the review, so if you're curious on how that one works, either watch the recording on that, which is up now, or look at the work solutions that I have. I've got work solutions to, I think I do actually for this, yeah, logarithms. Similar to these as well, right? But we'll put a pen in that one for now, if we're feeling okay with it. We will then move on to the sketching of the logarithm. Okay, so when it comes to sketching logarithms, just like with exponentials, how the base played a role in the shape of the exponential, based on 2 key possibilities for it, so too does the base of the logarithm. So if we think about the basic exponential, base greater than 1, that will result in this logarithm. However, if you had a base between 0 and 1, like the exponential, half to the power of x, you ended up having a reflection across the y-axis, or at least an effective reflection across the y-axis. So if the logarithm is to still be a inverse function, it should still be symmetrical about the line y equals x, and for that reason, instead of having a flip in the y-axis, because it is an inverse, it's a flip in the x-axis now. Instead of going from bottom to top right, it now goes top to bottom right. You get a flip vertically as opposed to horizontally. There's also a bit of mention as to like what the actual number of the base does to it. It pretty much just dictates how fast or slow it will wobble across it'll wobble. You don't really have to worry about that too much at all for your manual sketching. It's more so in your investigation stack if they ask you, hey, here's two coefficients, here's two bases, which one of them is going to do what, right? What's the intended behavior there? So this just sort of explores that. As you get closer to 0, for instance, it will shoot to its asymptote much faster, but also shoot across the right much faster, whereas a base getting closer to 1 will climb downwards faster and get to its asymptote slower. That's more, again, for the investigation type stacks. Same thing with the dilation factors, actually. This is another thing you don't really care about with tech-free. Just sketching it by hand. But they work the same way they always have. Bigger number stretches it more, smaller number stretches it less. The number at the front would stretch it vertically, the number in the bracket stretches it horizontally. The main thing you've got to worry about are going to be the reflections here. So again, because we have this base as an issue with creating an effective flip across the x-axis, or a vertical flip, it means we have a couple of different scenarios to work with. We have double the amount as opposed to any other graph. So here's our base greater than 1, just the green graph, log 2. If you have a negative at the front of it, all you're doing is flipping vertically, right? Just like what you have considered for all the other functions. Anytime you have a negative there, it is a vertical flip. So it makes sense that if your starting point was this green one instead, then when you flip that vertically, you get back to this thing. So you can see there's a duality between how this works. Essentially, the 1 over, the reciprocal of the base, will create the same pair of graphs. Similar thing going on here. Base greater than 1. If you have the negative on the x, you are flipping horizontally. Negative on the x, you are flipping horizontally with respect to whatever you started with. Translations, the only one that matters is going to be the horizontal translation, because that's going to be the location of your asymptote. So if you shift, because the natural logarithm, or the regular logarithm, has an asymptote at x equals 0, we just typically don't see it labeled because it's on the y-axis exactly. Whereas as soon as it's offset by that ever so slightly, you can now label that as its own unique asymptote. In this case, again, x minus a number shifts it right, x plus a number shifts it left. And you're essentially just setting the location of the asymptote with that. Vertical translations, I mean, yeah, they work the same as they always have, but you don't really have to consider it too much for the actual sketching by hand. So here's a summary of things that you actually care about for the sketching. You care about where the vertical asymptote is located, which is just going to be given by h, whatever the horizontal translation term is. For the x-intercepts, you're going to do that by setting y equals 0, and for the y-intercept, you're going to be doing that by setting x equal to 0, just like every other graph. As for how you actually do it, for the x-intercept, it'll often be the case that you'll flip to an exponential form. So you have this big nasty string of letters there. You're going to start by getting the logarithm on its own, so subtracting the c from both sides and dividing by a. Now the logarithm's on its own, you can flip to the exponential form, because the whole point is to get the x on its own for an x-intercept. From there, remove the d and plus the h. You'll see this more in an actual sequence of numbers. For the y-intercept, that ends up being a lot simpler. You literally just shove in your x equals 0, and whatever this comes out to be is what it'll be. Just remember, you cannot have a negative or a 0 in here. If you do get a negative or a 0, one of two things have happened. One is you've done your math wrong, potentially. Two is you've done your math right, and what you've done instead is prove that there are no y-intercepts. Because if you look at the graph, or at least any sequence of graphs here, none of these actually touch the y-axis. Right? Those didn't touch, this one did, but this one didn't. So it's only graphs that actually cross over in a certain way that could potentially touch the y-axis. So this is why knowing ahead of time what the graph might be looking like That's this step 3 here before we even bother solving for axis-intercepts. Identifying what the overall shape is going to be helps you save a bit of time, because you don't want to be plugging things into here and then realizing all along there was no intercept to begin with. So I've got a whole framework for this. Before we go through an example, are there any questions about anything I've covered so far? Alright, let's crack on. So, I've given you a nasty example here just to show you that it works for even the most complicated of graphs. If you look at what actually comes up in, especially the Unit 1 and 2 textbook, they're not nearly as bad. Like, it ends with just like, yeah, in fact it throws in a few exponentials as well. You get like a dilation or a translation, not like 10 different things going on at the same time. You might get a little bit of this in Unit 3-4, like a dilation plus a translation. But yeah. Anyway, first things first, in all of our sketching guides, we're going to start by making sure we have the general form of the function that we are trying to sketch. The reason why is because we want to be able to, at a glance, identify what are the relevant terms here. The only really relevant term that we care about so far is going to be the horizontal translation. Everything else we just solve via algebra, right? Like the horizontal translation gives us our vertical asymptote, but all this other stuff, we don't really care what it actually looks like. We're going to rearrange it for x or y anyway. So at a minimum, make sure we're revealing what the true horizontal translation is, which in this case is going to be making sure we take that coefficient off of the x, giving us a +5, so a shift left by 5. You might as well bring the rest of the thing through, right? Distribute that -3 through each of those terms. That way, at least then you know everything about it, as opposed to just the bare essentials. Now that we've done that, we can clearly see our asymptote is going to be shifted left by 5. So it's going to occur at x equals -5. If for whatever reason you forget that the horizontal translation is what's doing this, the other way you can go about it is to say, okay, the reason you ever have vertical asymptotes is for where things are undefined on the graph. So if I know that log a of 0 causes something to be undefined, what I can say is this whole thing in the brackets equals 0. What x would achieve that? And in this case, x equals -5 would achieve that, right? -5 plus 5 gives you 0, 2 times 0 also gives you 0. So we explore this in the maximal domain section as well, where the logarithm is only defined for positive numbers. So you just try to figure out, okay, where is it 0? And then just make sure it's everything but that. But okay, that's just another way of getting there, just in case you forget. It's the horizontal translation that does that. From there, any reflections we want to start looking at to make sure we understand the overall shape of the graph. This is going to tell us whether or not we should care about solving x and y intercepts or just x intercepts. In this case, we have a log of base e, natural log, and that is considered one of the like regular logarithms. It goes from bottom to top right. But we have a negative sign on the front. Negative sign on the front is a reflection in the x-axis vertical flip. So instead of going bottom to top right, it now goes top to bottom right. That gives us the overall shape, and whether you initially draw it to cut through quadrants 2, 3, 4 or 2, 1, 4, so whether you go like around this way or around this way, it still clearly shows you that you've got an x and a y that you need to solve for. And solving for those x and y's will tell you whether it curves shallow like this or deeper and cutting over that side instead. So you don't have to be too accurate with this, you just need to get a gist of what's going on. From here, now that we know we need to do both, let's do both. Y equals 0 for the x-axis, x equals 0 for the y-axis. So let's have a look at what that ends up looking like. Y equals 0, first step, get the logarithm on its own. Our goal is to finally get x on its own, and that's trapped in a logarithm. So, first thing we're going to do, get the logarithm on its own. Subtract 1, divide by -3. Logarithm is now on its own. From there, convert to exponential, because that'll free the brackets up of the logarithm. This is log base of e, so the exponential should have a base of e. It equals a third, so the power should be a third. The brackets are this, so the outside should be that. From there, rearranging is trivial. Just divide everything by 2 and subtract 5, and you get your x-intercept. You'll pretty much always have to do the exact form, but if they ask for a decimal, then by all means go ahead and do that. Y-axis intercept, much easier. Just shoving an x equals 0 into the function and then doing a quick evaluate. It'll usually be as simple as 2 lines because there's not too much else to do. Y is already on its own, so all we're ever doing is just simplifying a little bit. If you do have any domain restrictions, make sure you get those endpoints sorted. It's very rare to have that on a logarithm though, so I'm not going to look at that now. From there, just make sure you label where those should actually be. So, well, one of the things that comes up with this is, cool, I got these numbers, how the hell do I know that's a negative number and that's also a negative number? What do I do there? It tends to be easier to think about the exponential rather than the logarithm. We're more used to this naturally, less used to this one. So my focus goes here, figuring out whether this is a positive number or a negative number. You need to know that e is roughly 2.7. That's going to be important for this, because we need to do a rough estimate of whether this is going to be net negative or net positive. So if we replace e with roughly 2.7 and we're taking the cubed root of that, well, we're starting with a relatively small number and we are cube rooting it. So we're going to go even smaller than that. Furthermore, we're halving that number, so it's going to get even smaller again. From there, we're subtracting 5. So already 2.7 was less than 5 to begin with. We're only going above and beyond to make it even smaller and smaller and smaller, to make it clearly obvious that small number minus big number should be a negative result. So if that's going to be a negative result, we put it on the left side of our x-axis. From there, there's literally only one way to draw the graph. If it's got to go through here, then eventually it's got to go through here. You're not going to ever go whoop, whoop, and then go through here. It's just not going to happen. So in reality, you only have to care about what one of these terms are, and that'll allow you to solve the other one. Or at least place the other one correctly. Alright, that was a fair bit of talking. Any questions there? Sweet. Here's that bit on a domain restriction. Again, it's pretty rare for this to happen, but it's the same principle for all functions. It's defined from -3 to 5, inclusive of -3, exclusive of 5. All we ever do is shove in those x values into the function, and then that'll get us our endpoints. These both do come out as logarithms, so that's a bit challenging to know whether those are positive or negative numbers. So hopefully you've already drawn the overall shape of the graph to begin with, and then you're just sort of restricting within that domain section. If not, the next thing you'd probably have to do here would be flip that to an equivalent exponential form, and then go from there to evaluate, okay, is that going to be a negative number or a positive number? That's about it. Okay. Any questions at all on any of this? We'll do at least one example of the sketching, and then we'll see how we go for time. Any questions? Okay. Let's try... Yeah, why not? Just simply 1a over here. We've got y equals log 2 of x take 4. I've got a screen grab of the steps that we care about, should you wish to refer to those. How are we going to sketch this?
There's a horizontal translation
Mm-hmm. What?
of 4 to the right,
Yep, 4 to the right. What does that tell us about the graph?
translated 4 to the right.
Yep.
Um,
Yeah, so it is translated 4 to the right. What key feature does that tell us about?
it crosses the. Wait, no. It does. It does not touch the y-axis.
Yeah, so that will help you identify whether or not it touches the y-axis. You're combining that with a couple of different things. Namely, what you're probably doing in your head is saying, okay, shifted right by 4 tells you we have an asymptote at x equals 4. That's what that gives you. And then the fact that it's positive log 2 means it's just going to do that sort of thing, which is why you're probably saying it doesn't touch the y-axis, yeah?
Yeah.
Yeah, sweet. Okay, so that's a couple of things done back to back there. So we did, what step was that? That was step 2, getting our asymptote, and step 3, identifying the shape based on any reflections. So, you know, it was base 2, so it's naturally going to do that, and there's no reflections, so there's nothing else that would change it. Nice. From here, we can clearly see we don't care about the y-intercept, but we do care about getting this x-intercept. How do we get x-intercepts?
Set the thing to 0.
Yep, y equals 0, just like all the other graphs. 0 equals log 2 x take 4. Solving for x is going to be a matter of what? What are we going to do here?
X minus 4 is equal to 1.
Yep, so flipping to the exponential form, you got base of 2, power 0, which is why that's 1. And then whatever's in the brackets comes on the outside, leaving you with just x take 4 equals 1. Yep. And, well, this is just linear, so x equals 5. Quick sanity check. The x-intercept that we found is indeed to the right of our asymptote, as we expect. Nice and easy. As for answering the follow-up questions on this, so they asked for axis-intercepts asymptote, we already gave that. From here, it should now be fairly obvious to give the maximal domain of this. We're just going to look across and see what are all the x values that are valid for this graph. What x values does this graph span across? What are we going to have for maximal domain here?
Four to infinity, not including 4.
Yep, that's it. For infinity, non-inclusive on both of those. Perfect. Non-inclusive because that's an asymptote. We never actually hit the x equals 4 spot. Awesome. Any questions from anyone about that sequence there? Cool. All right. Well, that's graphing. It's very, very samey, especially in Unit 1 and 2. There's not a whole lot that changes. You might get some reflections, but other than that, it's basically a similar level of complexity. So maybe rather than do more of those, unless anyone wants me to, probably best to start looking at these other, like solving logarithm related stuff. Like, what's a good one? Probably 8, right? Prove that this nasty string of logarithms equals 0. I don't think we did that one in any of the classes. So let's see what we can do here. Practice our log laws of simplification. Log 10 ab squared over c plus log 10 c squared over ab, c squared over ab, minus log 10 bc that should all equal 0. Okay, so we need to prove that this all equals 0. How are we going to do it? big string of logarithms there, separated by pluses and minuses.
You can multiply and divide the
Yeah,
things.
that's right. Doing the product and quotient laws of it. Product for add, quotient for minus. Because they are, again, there's no coefficients there to stop us, so we're happy to just spread them all across because they all have base 10. So let's smack it all together. Log 10 of, now it's going to be big, so we got the AB squared part multiplied by the C squared, going to have the C from here and the AB from there. That is going to be minus that logarithm, which I'll now condense into it. Log 10 is going to have the A, B squared, C squared from before. It's minus this one, so it's going to be a division of BC. It's going to have that, C, A, B, and finally a division of BC. And this should equal 0. From here, it's just going to be a matter of everything getting combined into each other. So all these terms in here, we're just going to be practicing our index law stuff. So we can see we have a C on the bottom and a C squared on the top. We can see we have a B on the bottom and a B squared on the top. We have an A. So even before we even look at this division here, we now have log 10 of BC divided by BC. Well, that's pretty convenient. BC divided by BC, or in other words, as a fraction, BC over BC. Only one outcome for that. Log 10, 1, whoops. Log 10, 1 equals 0. Where you go from here, I think you just leave this here. You don't have to necessarily prove that log 10 of 1 equals 0. Maybe you could go 10 to the power of 0 equals 1, 1 equals 1, therefore I think you see this in like your university stuff, QED. I don't actually know what it stands for, and I might be using that wrong, but that's just a bit of trivia. You don't have to do this. You're probably fine to just leave it here. If you're really worried, you might go all the way to here, just to have a final, very obvious statement of true. How's that? Anything to clarify further? That was pretty much just a matter of using the log laws to smash everything together. Cool. We'll look at one that's a little bit different. Still probably using log laws, but how we get to a final answer is likely to diverge. So let's have, I think, 10a, I think might be a decent example. Log 10 x squared minus 2x plus 8 is equal to 2 log 10x. Okay, let's have a think. It's pretty much always going to start with log laws. Other half becomes x squared. Yes, it does. Right, you got 2 log 10x using the power law. You can bring that up to the x. Yes. Log 10 bracket x squared take 2x plus 8 is equal to log 10x squared. Awesome. We actually have an opportunity to do a little bit of a different approach here to solve this one. We don't necessarily have to do what we did before with combining all the logarithms down, which still works, but we have an opportunity here for something a little bit different.
remove the log base tens.
Yeah, remove long base 10s, exactly. So we looked at this a little bit with exponentials, where if we had like 2 to the power of x equals 2 to the power of x plus 1, because left hand side is very similar to right hand side, right? It's still just 2 to the power of something. What we say is that that bit doesn't matter, and it's only this bit that has an actual difference. So we just focus on x equals x plus 1. In this case, it's log 10 of this equals log 10 of that. Well, again, it's just right hand side and left hand side are both log 10 of something, so we don't actually really care what the logs at this point. It's just x squared minus 2x plus 8 is equal to x squared. This is now just solving a quadratic. In fact, it's even easier than that, because subtracting x squared from both sides gets you a linear. So you get minus 2x plus 8 equals 0, 2x equals 8, x equals 4. So that's a nice little exploration into not needing to go overboard with our log laws. We didn't have to, for instance, subtract this over this side and then do a quotient law, and then flip to exponential. It would have been a much longer process to do that versus just saying, okay, left hand side is very similar to right hand side. The only major differences between the sets of things were what's inside the brackets. You use this fairly often as well. Like, you can use this with roots, you can use this with all sorts of different things. Like I think I've seen a similar example of like square root of ax squared plus bx plus c is equal to root a bracket x take h squared plus k. Now, I mean, obviously you could just square root both sides of both sides of this and then get to the same spot. There was a similar. I'm not doing the question like total justice here. I'm doing it off memory, but there was a thing where you just say, well, okay, all I really care about is the similarity between this quadratic in quadratic form and this quadratic in turning point form, and you ignore the other bits surrounding it. But okay. That's that. Is there anything else here that's kind of crazy to do? I mean, this one's just a lot of numbers, but it's actually the same as question 8. Yeah, I guess I could show, maybe we can do f here. Because we have this constant of 1 in there as well, and it's worth showing a little bit about how you could handle that if you wanted to. 1 plus 2 log 10 x plus 1 equals log 10 2x plus 1 plus log 10 5x plus 8. So there's a couple ways you can handle this. The most immediate way is going to be to combine all the logarithms down. So left hand side we can leave alone for now. You can see there's a plus between these two, so we're going to product it up. Log 10 2x plus 1 5x plus 8. From here, if we want to continue combining logarithms down, we would now go ahead and subtract that. Oh, in fact, we probably should have put this in as a power. Let's do that as a line. 1 plus log 10 x plus 1 all squared. Cool. Now I can subtract that over. 1 equals log 10 of 2x plus 1 5x plus 8? Yeah, 8. And because it's subtraction, we do the division of the x plus 1 all squared. Now, the fact that there's a constant there doesn't actually really matter, because it's the only constant in the question. And so just leaving the constants over here, we have one big logarithm equals a constant. We can now flip this to exponential form. 10 to the power of 1 is equal to that whole string of insides here. That's one way of doing it. The other thing that the answers show in this actually is they say, nah, screw that. This looks like a big mess of complications. Which maybe I'll keep that there. Instead of doing all of that, what they're saying is this constant, you can actually write that as any logarithm that you want, because anytime the base and bracket are identical, the result is 1. So for instance, we know log 10 is just 1. So instead of writing a 1 here, what they've done in the answers is say, okay, let's just put that as log 10 instead of just saying 1 there. Now when you add that to log 10 x plus 1 all squared, this is now another product law that you can do. So that's going to end up being log 10 bracket x plus 1 all squared, and that's going to be equal to whatever was on that side, log 10 2x plus 1, 5x plus 8, 5x plus 8. And doing it that way means you don't have this big logarithm that you're now flipping to exponential. Rather, you have two slightly smaller logarithms that you can now do the approach we used before, which was saying, okay, well, this is just log 10 of something equals log 10 of something. Now I just kill logs. 10 bracket x plus 1 all squared is equal to 2x plus 1, 5x plus 8. Now you can see how this approach would still get there anyway, right? That you've just essentially divided the x plus 1 squared over in this approach here. Which just means that neither approach is wrong or right. They're very similar to each other. It's just a matter of how you think about the question. This is now quadratic. The only bit that I wanted to show you was different ways you could handle that constant. We can finish this if you like, although actually, you know what? Yeah, we're not going to have time to look at anything else. I'll finish this up, but before I do, I'm more concerned about, do you guys get the differences here? Like, do we understand the different ways you can handle when you have a constant there? Cool. Okay. This will just be a matter of expanding. So 10 bracket, and now going to have x squared plus 2x plus 1 is equal to, so 5, 2 is 10x squared, 8, 2 for 16x, we're doing that one, now 5x and 8. Cool. Expand this further, 10x squared plus 20x plus 10 is equal to, yeah, we can actually simplify this further, 10x squared, 16 and 5 for 21x, plus the 8. Quadratic parts cancel out, and yeah, we just continue from there. 20x plus 10 equals 21x plus 8. And lastly, well, that's a difference of 1, so you're going to have an x, that's a difference of 2, so you're going to have 2 equals x. Cool. Very similar, you'd get to the literally exact same spot here. You would just have to expand that quadratic over back to the other side, and then you get back to here. If there's no further questions, I mean, I'll still be around for a little bit if there are, but otherwise, thanks for coming, and I'll see you next time I see you.
Thanks, have a good day.
Thanks, you too.